Hello everyone, welcome to Patho Excellence. Do you know your microscope, or do you know how to choose and use the right microscope for pathology diagnosis? If answer is no, then this is a video you must watch before buying or using any microscope. You all know every pathology diagnosis begins with one instrument, the microscope. Yet, most students learn pathology without truly understanding it. And when you walk into a lab, you will see microscope priced at either rupees 30,000, rupees 1 lakh or 5 lakhs, even more. And no one teaches you why. Is it just the brand name, or is it extra magnification? So, in this video, we are not just learning microscope parts, we are going to understand why some microscopes are expensive. What is the complete anatomy of microscope? We will understand optics, lenses and objectives. What is numerical aperture and resolution? Measure and apply field of vision and follow correct microscope care protocols. So why PGs must master the microscope? Because microscope is equal to primary diagnostic tool in pathology. It is the third eye for pathologist. Errors in handling means errors in diagnosis, and examiners test conceptual clarity, not just identification. And foundation for histopathology, cytology and hematology is the microscope. So what is microscope? It is a scientific instrument designed to magnify objects far too small to be observed by the naked eye. It enables us to visualize the intricate details of cells, tissue, microorganisms and other minute structures. So how do microscope works? So it is basically utilize a combination of lenses to magnify objects. So light from an illuminator passes through the specimen. These lenses work together to bend and focus this light and create a magnified virtual image of specimen. So illumination, objective lens, eyepiece lens are key factors for any microscope. Now there are different types of microscopes available. So one is light microscope, which is most basic type. Second, electron microscope. Third is compound microscope, which we are using in our pathology section, and this is most widely used type. It is having multiple lenses to achieve high magnification. Fourth is stereo microscope. So it is for 3D view of the specimen. So these are just few examples of different types of microscopes. Now, all the microscopes share some common features and components. So one is magnification. So this is the ability to enlarge an object, typically expressed as a multiplication factor like 10x or 40x. Resolution means the ability to distinguish fine details between two closely spaced objects. And contrast, so the difference in brightness between the specimen and its background, crucial for clear observation. So you all know the parts of this compound microscope, starting from eyepiece, head, this is arm, these are the objective lenses, this is the mechanical stage, and here the illumination, light switch, base, fine adjustment and coarse adjustment knob, and brightness adjustment. So these are the basic parts of any compound microscope. So these are the parts from which you are very much familiar. But what is inside this microscopic parts? So that is the anatomy of microscope. So basically anatomy of microscope consists of, one is optical system, second is mechanical system, third is illumination system. So it consists of, one is eye point where eyepiece is here, there is a tube which is connecting eyepiece to objective lens, and here is the object. So this is the basic part of microscope. Now magnification depends upon the magnification power of objective lens and magnification power of eyepiece. So we have to multiply magnification of objective and magnification of eyepiece. Now let's start with the optical system. It consists of, one is ocular eyepiece, objective lenses, and the optical tube which is connecting this both the system. And whenever we see or we want to purchase any microscope, we have to see carefully microscope optical properties. So how will you judge whether these optical properties are good or not? So this is parfocal and paracentral properties. So basically parfocal means the image remains in a focus and it keeps the image sharp, and paracentral means image remains centered and it keeps the lesion found when, even if you change your objective. So what is parfocal? When the specimen is focused under one objective, it remains almost in focus when objective is changed to another magnification. Suppose we are uh, using 10x and we have focused one particular cell. Now we are changing it to 40x. Still we can see that particular cell without adjusting the coarse knob. So fine adjustment will definitely help us, and we will easily find the particular cell which we have seen in 10x view. So it saves time, it prevents loss of focus, reduces tissue damage, and essential for slide screening. And yes, good quality microscopes are parfocal, and cheap microscopes will have a frequent refocusing needed. So parfocality reflects precision in objective alignment. Second is paracentral. So paracentral means when the objective is changed, the same area of the specimen remains in the center of the field of the vision. So what is the importance? Suppose if we are using or this paracentral properties, and if we want to see mitosis, so we have to localize it, and even we change objective, it remain in the center of the vision. So easily localization of mitosis, easier study of organisms, faster correlation from low to high power, and indicates precise mechanical centering. Now let's see all the parts one by one. So first is eyepiece or ocular lens. So most commonly and widely used are wide field, which is WF, 10x, and located at the top. They are also available into 20x or 5 and 15. Wide fields are generally more than 14 to 16 number, which is field of view number, right? Then final magnification of image depend on the eyepiece. So here in this 10x suggests magnification power, 20 is suggest wide field of view. So this is the 20 is the field of view number. Then the diameter is 30 millimeter and dioptric adjustment is there. So whenever we want to purchase any microscope, we have to see this wide field eyepiece. May have pointer for teaching, antifungal and anti-reflected properties must be there. So ideal criteria: wide field, minimal distortion and good eye relief. So here there are two types of simple eyepieces, this Eugenean and Ramsden. So here these are called negative eyepiece and these are positive eyepiece. The difference between these two eyepieces are that both are having eye lens at the top and field lens, and the difference is the diaphragm is below the field lens in the this positive lens or Ramsden, and here it is the above the field lens in the Eugenean. But in our compound microscope for pathology, we are using wide field where there are number of lenses are more than this both the eyepieces. Like here you can see this is aberration free 10x eyepiece with diopter adjustment, where you can see multiple eye lenses. So, lenses like first is eye lens, this is lens doublet, triplet, one aperture is there and field lens doublets. So this is about eyepiece. Now what is diopter ring? The diopter between the left and right eyes varies from person to person. So this is the refractive power of eye which is must be corrected when we see under the eyepieces. So the diopter correction rings on the left and right eyepieces should be adjusted to the diopter difference of the observer to minimize fatigue during observation. Now objective lenses, very important part of microscope. It is the role of objective lenses is primary image formation. It determines resolution and clarity and it is mounted on this nose piece. So there are commonly used objectives are 4x, 10x, 40x and 100x. You all know 4x is for scanning and orientation, 10x for architecture and pattern, 40 for cellular details and 100x for nuclear as well as for organisms. Now let's see in detail. So what are objectives? They are the part of microscopes to provide magnified real image and perhaps the most complex component in microscope system because of their multi-element design. Available objectives having magnification range from 2x to 200x. Two main categories are there. One is refractive and reflective. So these objective lenses determines resolution and diagnostic clarity. Now in a refractive design, light passes through the system is refracted or bent by the optical elements, and each optical element is typically anti-reflection coated. So there is reduction in back reflections and improve overall light through output. And this design can range from two elements in a basic achromatic objectives and achromatic lens and a meniscus lens to 15 elements in plan apochromatic objectives. So plan apochromatic objectives are most complex high-end objective design with chromatic and flat field correction. Let's see. Basically, we are using refractive lenses which is infinite conjugate or infinity corrected. So 3 types. Basic one is achromat, plan achromat and apochromat. So apochromat is research purpose. We are generally preferred plan achromats because here is the difference. See, this is the lens showing achromat. So here the number of lenses are, one is lens doublet group here and this is lens doublet group here and this is frontal lens. In plan achromat, the number of lenses are more. So what happens? It provides flat field in the central area which is 90 to 95% of field of view. So if we use achromat lens, this is the field of view. If we use achromat lens, we can clearly see central portion of 65%, whereas with the help of plan achromat, we can use about 90 to 95% of field of vision which is having a flat. So rest of this area will show blurred vision. So blurred appearance is more if we use achromat. So we prefer plan achromat because it will produce flat flat view and we can cover most of the part of field of view. So plan achromatic objectives, they are commonly used in research and clinical setting. Plan means flat field of view and image appears sharp and in focus across the entire field of view. Well, achromatic which is related to color of the particular cell. So here this is a lens ability to produce images with little or no chromatic aberration, meaning the colors are not distorted or blurred. So when you choose microscope, always look at objective whether it is plan, achromat or not. So this is here the basic difference between different types of objectives. Now when you see objectives, there are some numbers written on objectives. So here you can see in this 40x, first of all you can see written plan, means plan achromatic lens, 40 which suggests magnification number, 0.65 that is numerical aperture. What is that? We will discuss later on. Then symbol is infinity, which is tube length, or 160 which is denoting tube length. 0.17 that is cover glass thickness we are using on the slide for the mounting purpose, and some lenses show WD, that is working distance, that we will discuss later on, and these all are having some color coding. So if 4x is there, it is having some different color according to the different manufacturer. So white denotes here 100x, blue is for 40x, yellow is for lower magnification. So these are the numbers written on the objectives. Now the most compound microscope having two standard system. One is the huge industry norm or DIN standard. Second is the Japanese industrial standard or JIS. So what is the difference between these two systems in optical tube? we can see here, this the DIN standard shows, this is the mechanical tube length. This is 160 millimeter, and here in the GIS standard it is 170 millimeter. Here the optical tube length means the distance between the lens and here the near the objective. So it is OTL, which is 150 here, it is here 146.5 mm. Another difference is parfocal distance, means the distance between the object and the objective lens here, which is 45 mm, and here it is 36 mm. So this is how these two standards are there. Now for finite conjugate, the microscope which are not having infinity correction, they use these two standard, DIN or GIS standard. While infinite conjugate, infinity corrected, where you find the light rays from the objective emerges parallel, image is formed only after a tube lens. So we will see in next slide what is the difference between infinite and finite conjugate. Second is object is near the objective, and infinity side faces eyepiece and camera. Now what are the key components? One is objective, and most important is tube lens, which is only and only present if infinity corrected microscope objective is there. Then how image is formed? So objective produce a parallel light, tube lens focuses light to form the real image, and final magnification depends on tube lens. So magnification formula is objective magnification is equal to tube lens focal length divided by objective focal length. So major advantage of this infinity corrected is it is insertion of filters, polarizers and beam splitters are possible. No image shift when accessories are added, and there is advanced microscopy systems. This is ideal, and we can use it for fluorescence microscopy, confocal microscopy as well as digital imaging system. Now, how will you identify whether your microscope is infinity corrected or not? There will be this symbol of infinity printed on objective body. So here you can see the both component, finite conjugate and infinite conjugate. Here you can see the light rays are directly going through objectives and focusing on eyepiece. Here there is parallel light rays, they are going from the objectives, passes through these extra microscope tube lens. So here it is absent, here this is the tube lens is there, and this is passing these rays to eyepiece. So this is how infinity corrected or infinite conjugate will help for better images. Now what is working distance? So WD is the distance between the front surface of the objective lens and the specimen when the specimen is in a sharp focus. So this is called working distance. So scanner which is 4x having highest working distance, here may be depending upon the lens length 20 to 30 millimeter, and oil immersion will have lowest or very short working distance 0.12 to 0.2 mm, low power having 5 to 10 mm, and 40x having 0.5 to 0.7 mm. Now another part is of mechanical system. So mechanical system consists of, we all know, head, body tube, revolving nose piece, stage and mechanical stage, coarse and fine adjustment knob, arm and base. So all the functions having uh, its role when we use microscope for the diagnosis. So head having different types like monocular head, binocular or trinocular head. Revolving nose piece, it holds objectives, allows change of magnification. It click stop alignment, ensure optical axis. Stage, which is a platform where slide is placed and central aperture allow light passes. Mechanical stage, which is having X and Y movement. Precise slide positioning is very important in reporting. Now adjustment knobs like coarse adjustment, which is for rapid focusing, use only with 4 and 10x. Fine adjustment, it is used for precise focusing and used with 40 and 100x, and this is for nuclear details. Arm and base for support and for stability. Now third system is illumination system. So illumination within a microscope is just as important as selecting the proper eyepiece and objectives. So it composed of light source, now LED preferred, condenser and iris diaphragm. So its function is controls brightness, contrast and resolution. So we have seen this objective and eyepiece. Now illumination consists of this part. So this is condenser and illumination, and this is the color illumination setup where you find both the system. So what is that? It is also called bright field illumination. So this is a specific type of backlight illumination, and here in this color illumination, incident light from the illumination source such as light bulb uh, with the light from behind, it employs two convex lenses. One is the collector lens and another is the condenser lens. And since the backlight illumination floods the object with the light from behind, it is also known as bright field illumination. Second is a dark field illumination. So here this is design which forces the light to illuminate the object under inspection, but there is it not to enter to optical system. So here you can see this is the block here, and there is no light entering from behind, and it is basically important for transparent object. So this is called dark field illumination setup. Third is epi illumination setup. So here the light source is above the objective. So what happens? The objective and epi illumination source substitute for a color illumination setup, and using the objective for a large section of the illumination makes epi illumination very compact, and this is a major benefit of this design, and this is used for fluorescence application. Now condenser and iris diaphragm. So here you can see this is the objective, this is the specimen, and here the condenser. And condenser focuses light on the specimen, while iris and diaphragm regulate the light cone and adjust for the best contrast, not for the maximum brightness. So there are different types of condenser. One is commonly simplest and least corrected is AB condenser. Another is aplantic, achromatic, aplantic, achromatic. So both all these condenser having spherical aberration and chromatic aberration uh, in a different manner, like aplantic having a spherical aberration, while this aplantic and achromatic having both spherical and chromatic aberration. And AB condenser having numerical aperture up to 1.4 in the best model with 3 or more internal lens element. Now what is numerical aperture, which is written only on the objective lenses? So this is a light gathering ability of an objective lens and it determines resolution. So what is the formula? Numerical aperture means number which is a refractive index of medium n into sin theta. So refractive index n of air is 1, immersion oil 1.515 and glass it is 1.52. So oil increases and hence it increases numerical aperture. Now theta, angle of light. Wider light cone means higher sin theta. So it is achieved by proper condenser height, correct iris diaphragm opening. So numerical aperture and resolution, which is resolution D is equal to 0.61 into lambda divided by numerical aperture. So wavelength of light, which is 550 nanometer for green light, and if higher numerical aperture, it is equal to better resolution. So higher numerical aperture is equal to smaller resolution and which is smaller d and better resolution. So there are different numerical aperture for different objectives, like for 4x it is 0.10, 10x 0.25, 40, 0.65 and for oil immersion it is 1.25 to 1.40. So why oil immersion improves resolution? Because its reflective index of oil, which is 1.515, is equal to glass, which is having 1.52. It prevents light refraction loss and allows more oblique rays. So there is increases numerical aperture but not magnification. So why it is required? Numerical aperture, if it is high, it is essential for nuclear chromatin pattern, mitotic figures, bacterial fungal parasites identification, and malignant versus benign nuclear features are more visible with high resolution, which means increased numerical aperture. Now field of vision. So field of vision, if we say in simple words, it is how much tissue you can see at one time. So it is the diameter of circular area of specimen visible through the microscope at a given magnification, right? So what determines field of vision? It is the eyepiece, most important. We have already seen that field number is written on eyepiece, whether it is 18, 20 or 22. So higher field number, larger field of vision. Objective magnification. So if it is increases, field of vision decreases. So here you can see in low power view, magnification is low. In high power view, magnification is high. But field of vision, which is lower in this high power and higher in low power. Third is tube lens and microscope design, which is infinity corrected, will give uniform field of vision with and minimal distortion. So basically 4x having large field of vision, 100x having very small field of vision. So you can see here, this is magnification, wide field, and this is field number. So if 20 is field number, the visible area is 2 mm. How to calculate? So field of view in millimeter is equal to field number, which is 20, and objective magnification whichever we are using. If we are using 10, so it is 2 mm. If the eyepiece field number is 18, and if we are using 10x objective, then it is 18 divided by 10, 1.8. And suppose we are using 20 field number, 40x objective, so 20 divided by 40.5 millimeters. So how you can identify field of view? So field of view or field of vision, you can say here you can see if field number is 20 but objectives are different, then field of vision will be changed. So for 4x it is 5, for 100x it is 0.2. And here the same objective but different eyepiece, the field of vision will automatically different. So here in this figure we can see field of view is equal to field number of eyepiece divided by objective magnification. Now what is the application of this field of vision? So it is for cell and nuclear size estimation, glomerular diameter, that we'll see in next slide, tumor thickness measurement, and parasite identification. So now how to measure field of vision using stage micrometer. So this stage micrometer is available commercially. It is intended for routine calibration of light microscope when alternating objective of different microscopes are there. So here this stage micrometer having 1 millimeter divided into these 100 parts. So each division is 10 micrometer, right? And another is ocular micrometer or eyepiece micrometer. So it is a glass disc of 21 millimeter, and it is having this graduated scale in the center of the disc, and it is placed into eyepiece lens on the top of the field diaphragm, and this will not change size when you change the magnification, right? So now I want to measure specimen size under the microscope. So what should I use, whether ocular micrometer or stage micrometer? So basic thing is, when you want to measure specimen size, you will have to use ocular micrometer, and stage micrometer, it is to check magnification errors of objective lens, right? Now how to use ocular micrometer? So this is a graduated round disc where its single division width of this ocular micrometer, how you will calculate? It is the actual width of the single pitch or division divided by objective lens magnification, right? So this ocular micrometer having 10 millimeter x and y. So 10 millimeter means 1 centimeter divided into 100 divisions. So 1 division is equal to 100 micrometer. So here you can see this is a ocular micrometer scale where you can identify number written on it, 20, 30, 40, 80, right? Now we have to use formula that single pitch width is equal to this 100 micrometer divided by the objective lens we are using. If 20, it is 5 micrometer. Now here this is a glomeruli, and if we see from this image, we can see the glomerular dimension having 23 horizontal and 22 vertical division, because it is starting from here 40 to 63, and here it is 40 to 60. So number of these pitches are 23 here, 22 here. Now our pitch width is 5 micrometer. So we have to multiply 23 by 5, so 115, and here it is 22 by 5, so 110 micrometer. So the measurement of glomeruli is 115 by 110 micrometer. So how you demonstrate, identify, measure size of kidney glomeruli. So this table shows objective lens which is having magnified pitch width according to the uh, objective lens magnification. So 5x having 20, 10 is having 20 micrometer, 20 having 5, 40 having 2.5, and likewise 100 having 1 micrometer. So we have to do it by 100 micrometer divided by this number of objective lens. Now we want to calibrate. So how will you calibrate the objectives? So here we have to use both ocular and stage micrometer for calibration. So as we know, stage micrometer having 1 millimeter divided by 100 division. So each pitch having, or each division having 10 micrometer size, and ocular micrometer having 10 millimeter. So each division having 100 micrometer. Under the 20x objective, if we see, so here we can see this is a ocular micrometer vision. So this is the 100 micrometer per division. And if we see under 20x, this stage micrometer pitch having a 10 micrometer size. So expected measurement must be, if 10 pitches on the stage micrometer, like this is 110, and it should match 20 pitches on the ocular micrometer. So here it is, here you can see this is the ocular micrometer, and here it is a stage micrometer. So there is a observed measurement. If we see, the ocular micrometer reads 22 pitches instead of 20, right? So here you can see these are the different, it must be up to here, right? So here there is a error. So here instead of having 20, you can have this the 22 measurement. So we have to correct this measurement value, like it is actually 20 but we are getting 22, so its correction factor is 0.91. So whenever we get actual measurement value, we have to use ocular micrometer reading into 0.91 for precise result. Now how you insert this eyepiece ocular meter, here this is the diagram showing how to put them into the eyepiece. Now if you want to purchase the microscope, you have to see all the parameters that we have discussed earlier. So let's revise. We have to first of all see optical system. So whether it is binocular or trinocular head, according to your need. Binocular is having less eye strain, and trinocular is helpful for photomicrography and for teaching. Always use plan objective, means flat field, or plan achromatic, mostly 4, 10, 40, 100. Use with high numerical aperture and plan achromatic correction, which is important. Then eyepiece, which is wide field, 10x is uh, very helpful. Resolution and image quality, it is good resolving power, having not just magnification is important. Minimal chromatic and spherical aberration, so in the form of a good condenser. Uniform illumination across field, and clear nuclear and cytoplasmic detail must be there. So we have to see parafocal and paracentral microscopic optical properties check when you see the or when you purchase the microscope. Illumination system required is built-in LED illumination, which is having uniform long life and low heat, adjustable condenser with proper alignment, and iris diaphragm for contrast control. Now mechanical stability and ergonomics, if we see stable vibration free base, smooth course and fine focus for micrometer with micrometer precision, proper X and Y movement of mechanical stage, comfortable viewing angle for long reporting hours, and yes, oil immersion capability, which is high quality 100x, easy cleaning, oil resistant lens coating, and good working distance. Durability, robust construction for heavy daily use, easily available service support, and spare parts are very needed. Warranty and AMC options are very much important. Teaching and documentation support in the form of pointer eyepiece, which is useful in teaching and exam. Trinocular port for camera attachment, and compatibility with digital imaging system. So whenever you purchase, you correctly see all the these parameters, and you purchase accordingly. Now, how will you carry your microscope? Because it is very much important, because it maintains resolution and numerical aperture. It prevents artifacts, and it also prolongs instrument life. So, what are the steps, or what are the care steps you have to take before and during use? First is start with 4x objective. Second, increase magnification gradually. Adjust condenser and iris properly. Avoid force on knobs. Then oil immersion care. Use recommended oil only, and clean oil immediately after use. Third is never rotate dry objectives through oil. Now what refractive index you will use of oil is 1.515. Viscosity, it influences application and stability. High optical clarity is essential for resolution, and always use oil designed for microscopy. Do not substitute with cooking or cosmetic oils. Cleaning and storage, use lens paper only. Clean in circular motion. Cover microscope after use, and store in dry dust free area. So lens paper is generally preferred. You can use 70% alcohol or lens cleaning solution, and optional is xylene alcohol mixture if recommended by manufacturer. And what are the common mistakes? Like leaving oil overnight, or using coarse focus at high power view, excessive light, and improper storages are not beneficial. So avoid all the mistakes. So these are about how you know your microscope, what are the things you will see when you purchase your personal microscope, right? And I hope now you see um, microscopy easy when you purchase the microscope according this guide. And